All right. Good morning, everyone. How are we doing? Absolutely. If a question is asking you to find the limit of a Riemann sum, you know that if your function is Riemann integrable, which I assume the question assumes that, then all you need to do is find the integral. If you can equate it to an integral, then all you have to do is find the integral any way you want. Yeah, I think I'm gonna start doing a minute or two of songs while we wait. The midterm is open for 72 hours. We haven't decided on the date yet, but I want it to be before. The break. Which hour would this be? I'm not sure what that means. What song was that? This was Harmonium. A tremendously famous band from Quebec, who actually just released right now a symphonic remake of one of their, I want to say of an album, but it might not be an actual album. It might just be a collection of songs. Anyways. All right. How are we doing? Look them up. They have an amazing bunch of albums. They were so famous in the 70s that they were, all their songs are in French, and they were invited to tour California. Are you gambling on the stock market? Is everybody checking out what's happening with GameStop? GameStop, rather, GME. Is that what everybody's gambling on today? Yeah, to the moon. Indeed. Weekend was all right. Today we're going to do a bit more U substitution and move on to another technique known as integration by parts. I do speak French, yes. French is my mother tongue. All right, let's say a few examples. This is stuff we were doing last time, just to get us back into the swing of things. We are skipping chapter 6 for now. Yeah, they have Dixie, absolutely. So, a few examples before we move on. Right? What are we going to do here? Did anybody buy GME? I did not. I mean, I feel I should. Maybe just a few shares just for fun, but all right. What are we going to do? Yeah, I don't know about options. You know what to do, right? What's the idea here? You know, I mean, maybe a first thought would be to make a U substitution, U equals 1 plus 4, 1 plus x to the 4. And it's tempting. It's tempting. And let's try that. If U is this, then du is 4x cubed dx. And the problem is we don't have an x cubed, right? We have an x, and that's very problematic. So this is not the way to go. This doesn't work. Instead, as Yuan Ming suggests, U equals x squared. Now, where is this coming from? This is coming from the fact that you have an x here, which you know to be the derivative of x squared to within a constant. That's the idea. If U is x squared, then du is 2x dx, and x dx you have right there. So this x dx is 1/2 du. So if you do that, this x dx becomes 1/2 du, and then you're left with a 1 over 1 plus x to the 4. But u is x squared, so this is really 1 over 1 plus u squared, whose antiderivative you know, exactly as was suggested by a few people. This you recognize as arctan u plus your arbitrary constant. So 1/2 arctan of x squared. There it is. So while it might have been tempting to try this, it doesn't work because you don't have an x cubed. How are you? Let's try another. How do we remove the x in the numerator? Well, the x dx here is 1/2 du. Right, so Sophia is asking the same question. You always start with the derivative, right? So the x dx here is 1/2 du. And then we're left with a 1 over 1 plus x to the 4. But x squared is u. So x to the 4 is u squared. And you're done. Everybody with us? Consider this. What are we going to do? Let's try u substitution. U equals x squared plus 1. So that du Stefan is suggesting, could we have separated this into the integral of x over 1 plus x over x to the 4? And the answer is no. That's not how addition of fraction works. No, because look, I mean, if you say 1 over 1 plus 1, you know that to be 1/2. It is not 1 over 1 plus 1 over 1. Here I'm suggesting, thank you everybody, a u substitution. Everybody's pointed out that du is 2x dx. So 1/2 du is x dx. But now you're thinking to yourself, we don't have an x dx, we have an x cubed dx. Well, this x cubed, you can split into an x and x squared. And now the x dx, this becomes a 1/2 du. U is x squared plus 1. So this becomes the square root of u. And now you have x squared left outside. You don't want equation, an integral with x's and u's, but as a few people have pointed out, x squared is really u minus 1. So this x squared is u minus 1. Exactly that. And now, if you expand everything, everything is easy to integrate. Let's take the 1/2 outside. This is u to the 3 over 2 minus u to the 1/2. Integrate. Integration is trivial. Antiderivative of u to the 3 over 2. 2 over 5 u to the 5 over 2. Antiderivative of this. 2/3 u to the 3 over 2. Add in your arbitrary constant. Rewrite everything in terms of x, and we're done. Exactly. Power rule, which is trivial, right? If you don't agree with that now, you will agree with it in a week or two. So is there a rule to determine u? There is not. There is not. There is not. I was going to point out that you can, of course, verify that this is the right answer. Is it 1/2 in the final line? What do you mean? I've multiplied the 1/2 throughout, canceling with each of the 2's in the numerator, right? I will leave you to verify that this is the right answer. Right? You know what to do. If you differentiate that, you should be able to get back to what you started out with. Absolutely, as FE suggests, it gets easier the more problems you do. And you have to do lots and lots and lots of exercises. All right. I think we're comfortable with the u substitution, at least when it comes to an indefinite integral. Now let's ask the question, what if you have a definite integral? You do develop intuition, absolutely. What is the power of u in the last line? 5 over 2. And 3 over 2. Right? It's just the antiderivative of these two. You know the power rule. Absolutely right. I mean, first of all, how do we evaluate this integral? We're going to do a u substitution. Your thoughts? U equals? Right, so I mean, before we were doing u substitution with just an indefinite integral, no bounds. Here we have bounds. We'll see how this differs. People want to suggest root x. Nothing wrong with that. Nothing wrong with that. We can take it a step further though. I would suggest a 2 plus root x. Absolutely. If u is 2 plus root x, then du is 1 over 2 root x dx. And let's bring the 2 to the other side. So 2 du is 1 over root x dx. And 1 over root x dx is exactly what you had here. How do we get 3 over 2 as the exponent on the second, the last line? So from here to there. Oh, this one here? I assume you mean this one. This was u to the 1 times u to the 1/2. We expanded, right? We multiplied this out. And we get a u to the 3 over 2. So this is 2 du. And then we're just left with the square root of 2 plus root x, which is just square root of u. You can take constants out of the integral, absolutely, because you know the integral is linear, because you know the derivative is linear. It's true for the derivative, so it's true for the antiderivative as well. Absolutely. Right? The integrand becomes 2 root u. What about the bounds? Well, since the whole integral is in terms of u, it makes a lot of sense to change the bounds in terms of u as well. Here you had x equals 1. But when x is equal to 1, u is equal to 3. And when x is equal to 4, root of 4 is 2, 2 plus 2 is 4, u is also equal to 4. So if you make a u substitution, you can change the bounds and keep working from there. An alternate approach is to leave the bounds in terms of x. But in that case, you're going to have to rewrite the antiderivative in terms of x because the bounds are in terms of x and not u. Here, the nice thing about changing the bounds is that when you take the antiderivative, what is the antiderivative? 4 over 3 u to the 3 over 2. You can now just plug in the bounds. You can plug in the bounds because these bounds are in terms of u. So you get 4 over 3. Square root of 4 is 2. 2 cubed is 8. Minus 3 to the 3 over 2. If you had left the bounds in terms of x, and let's revisit that. If instead you made the same u substitution, right, getting the same integrand as before, but left the bounds in terms of x. Let's leave the bounds in terms of x. If you take the antiderivative, still the same antiderivative, 4 over 3 u to the 3 over 2. But now you are not allowed to plug in the bounds because the bounds are in terms of x. So you have to rewrite your u in terms of x. And this is 2 plus root x to the 3 over 2. And now the bounds are in terms of x. Now you can plug in. Well, let's see what happens if we plug in. Square root of 4 is 2. 2 plus 2 is 4. Square root of 4 is 2. 2 cubed is 8. And then when x is 1, you get 3 to the 3 over 2. Exactly the same answer as before. Right? It makes a lot of sense that the answers would agree. Where did this come from? By plugging in the bounds. You plug in the top limit, subtract plugging in the bottom. How did we know to change the bounds? Well, we have two options. If you're making a U substitution, it makes a lot of sense to change the bounds so that everything is in terms of U. Or, as we showed over here, an alternate approach is to leave the bounds in terms of the original variable, but then you have to rewrite everything in terms of the original variable x before plugging in. So on the right, I left the bounds in terms of x, but then I had to rewrite everything in terms of x before plugging in. In the one on the left, I did everything in terms of u. They were suggested. Mods were offered for this, but I mean, I was afraid that it was going to be so boring for a student to sit there for an hour and a half just deleting a few messages that I figured I'll do it. If it becomes overwhelming at some point, we'll get mods, but otherwise. Well, I mean, as you see, the answers agree, and they always agree. What does it mean? What does it mean? It means geometrically, here you were on the line. I mean, originally you were on the interval 1 to 4. On the real line 1 to 4. Here it means that you're actually working on a curve. That's geometrically what's happening, but it's not that important. What's important is the technique and the fact that you have options at this point. You can decide to change the bounds or not, and that's really up to you. Let's take another example. Yeah, exactly that. Consider this. What are you going to do? You recognize this as being very similar to the first question we did. Very nice. U equals e to the x. U equals e to the x, so that du is e to the x dx, and that's exactly what you have here. Very nice. So that this e to the x dx becomes du, and here this e to the 2x you treat as e to the x all squared. So this is 1 over 1 plus u squared. And while we're here, let's change the bounds. If x is 0, u is 1. And if x is 1, u is e. So that now we're working with this integral, and you never have to go back to x. Again, arctan was suggested. You saw that coming. Arctan between 1 and e. And so we get arctan of e minus arctan of y, which you know to be pi over 4. You always plug in the bottom and then the top bounds when changing the bounds. Well, I mean, all I'm saying is when x is 0, u is 1, and when x is 1, u is e. Again, I like to change them, but an alternate approach is to leave them in terms of x, but make sure that you know what you're doing. Make sure you know what you're doing and that you don't mix up the two approaches. If you're doing one approach, what do I mean by that? If you're leaving the limits in terms of x, don't plug them in for u. If you're changing the limits to u, don't rewrite this as x. Could you have used 1 plus e to the x? I don't think that would have worked very well here, because you don't have a 1 plus e to the x. You have a 1 plus e to the 2x. Questions? Where did the arctan come from again? Antiderivative of this. Antiderivative of 1 over 1 plus u squared is arctan u. Because you know the derivative of arctan u is 1 over 1 plus u squared. Where did the e and 1 come from? From the bounds. Everybody with us here? All right. Consider this. Michael suggested to make a u substitution. U equals x squared. Absolutely, let's do it. So that du is 2x dx. And x dx is exactly what you have here. So that this becomes the x dx is 1/2 du. This function, f of x squared, is f of u. And let's change the limits. When x is 0, u is 0. And when x is 3, u is 9. And if we take the 1/2 outside, Here you have the integral from 0 to 9 of f of u du versus the integral from 0 to 9 of f of x dx. But u is just a dummy variable here, right? Whether it's the integral of 1 over 1 plus u squared du from 1 to e, or whether it's 1 over 1 plus x squared dx from 1 to e, it's still the same answer. So it's still the same integral. Still the same answer. So this is 1/2 times 4, which is 2. How are we doing? And this is the type, well, this is one type of question you can expect on the midterm. We switch the bounds because we can switch. Don't think of u as a function of x in here, right? What I mean by that is, look, I know a lot of people are wondering how this integral can be the same as that integral, because you have x's and u's, and u is actually x squared. So isn't it different? The answer is no, because you see the integral from 0 to pi over 2 of cosine x is the same as the integral from 0 to pi over 2 of cosine u. Whether it's u or x, it's just a dummy variable, right? Here, you'll have an antiderivative of sine x between 0 and pi over 2, which is just 1. And here, you'll have sine u between 0 and pi over 2, which again is just 1. Here, u might have been some totally crazy function of x, and it doesn't matter. Doesn't matter what happened before, you're now just dealing with this. So whether it's the integral from 0 to 9 of f of x dx, or the integral from 0 to 9 of f of u du, it's the same thing. How are we doing? We had the integral from 0 to 3. We made a u substitution. It became the integral from 0 to 9. These are very nice questions. The problem is, the reason they're nice is, integrating websites like Wolfram Alpha and everything else doesn't know how to deal with those. This 4 was given here. Questions? All right, let's consider a nice example that is very useful for this course and subsequent courses as well. Let us recall function f of x is said to be odd, a function f of x is said to be odd if f of negative x is negative f of x. Right? We saw that in Cal 1. An example of that, the function 2x cubed minus x. Right, if you plug in negative x instead of x, this is negative x cubed minus negative x. And negative x cubed is negative x times negative x times negative x, which is negative of x cubed. And if you factor out a negative from that, this is 2x cubed minus x, which is negative of the original function. Right? You've seen this before. Here's the claim. If your function is odd and Riemann integrable, on the closed and bounded interval a negative a to a. I mean, it's not new. We're still using the U substitution. If you have an odd function that's Riemann integrable on the interval negative a to a, then the integral from negative a to a is 0. It's a new result. We haven't seen it yet. We'll prove it right now. The proof is very nice and simple. Was it proven in the tutorial? Let's prove it. The proof is nice and simple. It's just a nice application of the U substitution. Well, let's do it. I mean, it's nice to revisit. Isn't this just common sense? Maybe, but there's a nice proof. There's a nice proof, which is just a simple U substitution. So let's prove it. This is the integral from negative a to 0. I mean, by properties of the integral, right, we can split that up. By properties of the integral, you can split that up. And now, let's make a U substitution. Let's make a U substitution on that first integral. Let's make a U substitution on that first integral. So we're just going to concentrate on the first integral. And we're going to make a U substitution. U equals negative x. To make use of the fact that your function is odd. If U is negative x, then du is negative dx, or negative du is dx. And what does the integral become? If you switch the limits on the first integral, you mean switching them like this, flipping them. You get the integral from 0 to negative a with a negative outside, but this is the integral from 0 to a. So they might not be the same. They might not be the same. But if you make a u substitution, dx is negative du. F of x, right? Your x is actually negative u, so this is f of negative u. And let's change the limits while we're here. If x is negative a, then u is a. And if x is 0, u is 0. Very nice. So this is the integral from a to 0. Now let's make use of the fact that f is odd. F of negative u is negative f of u. And then the two negatives cancel, giving you a positive. But now you've got the integral from a to 0. So you can flip that by putting the negative outside. And there you have it. So this integral is actually negative of the integral from 0 to a of f of u du. And then if you add the integral from 0 to a of f of x dx, by the same idea we had before, right? Now u is just a dummy variable, same as x. So this integral and that integral are the same. This one's negative, this one's positive. They add to 0. A very nice, simple application of the u substitution. What is wrong with keeping negative a to 0? Well, it's not immediately clear that this and that one cancel out. And they don't cancel in general. Where did the second negative go? These two negatives canceled out to give you a positive. So they canceled out here, right? So now you have the integral of f of u du. And if you switch the limits, you get another negative. Let me leave you with the following claim that you can prove in exactly the same way. If f of x is even and Riemann integrable on the interval negative a to a, then the integral from negative a to a of f of x dx is twice the integral from 0 to a. We had the integral from negative a to 0 here, and we made a substitution, u equals negative x. So when x is negative a, negative a, u is equal to a. And when x is equal to 0, u is equal to 0. We're changing the bounds following a u substitution. Exactly what we were doing before. Questions here? Do we want to take a moment to prove the claim I suggested a while back? Namely, when we are dealing with Riemann sums, if you have a limit of a Riemann sum and you want to express it as an integral, we suggested that you could always take the interval to be 0, 1. Shall we prove it? We're in a position to prove it now. Suppose you had the limit of some Riemann sum so f of xi star delta xi, right? So the limit of a Riemann sum, and we suggested that this was equal to some function, to the area underneath the graph of some function on some interval AB. My claim to you was that you can always take the interval 0, 1. Can I explain how I got the 0? This integral here is the same as this integral here, right? Because the u or the x is just a dummy variable. We showed that, right, with the cosine integral. Integral of cosine u between 0 and pi over 2 is the same as the integral of cosine x between 0 and pi over 2. X or u are just dummy variables. So this is some real number because your function is Riemann integrable. This is the same real number, but it's negative. So they add to 0. Consider this. Suppose that you have this limit of a Riemann sum equal to some integral on the interval AB. My claim is that you can always take A to be 0, B to be 1. And let's prove it now by making a simple u substitution. We're going to make a simple u substitution. U equals x minus a over b minus a. Let u be x minus a over b minus a. All I'm doing is I'm making a u substitution. Then du is easily seen to be 1 over b minus a dx. So bring that to the other side. And here you can solve for x. X is actually b minus a times u plus a. So now let's look at what happens to this integral. So that integral, the integral from a to b of f of x dx, which is what our Riemann sum was equal to. What does that do? Your dx is b minus a du. F of x is this. B minus a u plus a. And let's change the bounds while we're here. When x is a, x minus a minus a is 0. And when x is b, b minus a over b minus a is 1. And we're done. We're done. We have the integral on the interval 0 to 1. You can always assume your interval is 0, 1. How are we doing? Where did the x minus a over b minus a come from? Or why did we choose that value of u, right? Yeah, exactly. So we just proved they always assume 0, 1. Exactly that. Harry doesn't understand why we're done. We were trying to show that you can always assume the interval to be 0, 1. So here, given any integral, I've related it to an integral on the interval 0, 1, which is exactly what we were trying to do. Which is exactly the claim I had made before. You can always assume it's the interval 0, 1. If we assume 0, 1, does our function have to take that form in some way or another? Do you mean this form? Probably not. I mean, you can... The thing is, well, short answer, yes. Short answer, yes. You don't have to go back to this one. I'm saying you can always take the interval 0, 1. Where did you write 0, 1 in the claim? I didn't even write the claim, right? I mean, the claim was that you could always take the interval 0, 1. What did you write in the parentheses in front of f? It's really f of x, right? So x was this. I just wrote this in for x. F of b minus a times u plus a. Exactly what x is. Why do we want to be able to assume the interval 0, 1? Because it makes life easier. Not always, but in a lot of cases, right? Because if you're given a Riemann sum, right, and you know, I was talking to Ibrahim last week, a student in our class. He was suggesting that you have to reverse engineer, and I mean, it's a nice way of describing it, right? You have to reverse engineer what function gave rise to this Riemann sum, right? You're reverse engineering, you're finding a function, an interval, a partition, and which points. It's a lot of things to come up with. I'm suggesting that you can always assume it's the interval 0, 1. So that takes care of one of the 4 things you need to find. Where did we get the u from? I mean, it's a valid question. Who knows how that first person came up with that? The idea is that this transforms any interval AB into the interval 0, 1. We're going to revisit that later on. This is going to come up naturally in the Cal 2 version of the mean value theorem. All right, we have to move away from this because we haven't really done anything new today yet. So let's move on. Omar is suggesting it's difficult to go from a Riemann sum to an integral, and it is. You need practice. But you see, this claim now suggests it removes 25% of the work. It says that you can always use the interval 0 to 1. All right, moving on. Moving on. Moving on. We're able to do more difficult questions now, right? This U substitution helps us tackle more difficult questions, more difficult antiderivatives, but we're still not able to do something like this, right? We're still not able to figure out the antiderivative of that. If this x wasn't there, though, then the integral would be very easy. How can we get rid of x? We can differentiate it. The derivative of x is 1, it's gone. How can that be done? Let's recall the product rule from differential calculus. And as Shamir suggests, it is a reverse product rule. Exactly. The technique we're going to introduce right now is the reverse product rule. It's the inverse operation to the product rule. What is the product rule from differential calculus? What is the derivative of the product uv? You know what it is. You differentiate the first one, leaving the second one fixed, plus you leave the first one fixed and you differentiate the second one. That's the product rule you know and love from Calc 1. Integrate. If you do the same to both sides, equality is maintained. So integrate both sides. What is the antiderivative of the derivative of uv? Or what function has as its derivative the derivative of uv? Of course, that is uv, because the derivative of uv is the derivative of uv. If you bring this to the other side, we get the formula. The integral of u dv is uv minus the integral of v du. This is known as integration by parts. The integration by parts formula, which, as was suggested, is the inverse operation of the product rule. In very much the same way that the U substitution was the inverse of the chain rule. Somebody's asking why are we using D instead of the derivative symbol, instead of the prime, only to make a connection between this kind of thing, right? This notation, which becomes very important here. No inverse quotient rule. I'm sure you knew that. Let's take a few examples. Well, first of all, let's leave the integration by parts formula in this way, and you'll understand why we're writing it like this. Let us consider this. Again, you cannot find the antiderivative using a u substitution here. It's not going to happen. But you're thinking to yourself, if I did not have this x, the integral would be very easy. How can we get rid of the x? We can differentiate. Let us rewrite this integral as the integral of u dv. So let me choose u to be x. And consequently, if the integral is u dv, this is the u, everything else has to be dv. Sorry. dv has to be everything else. dv has to be e to the x dx. We have skipped chapter 6. We're now in chapter 7. This is 7.1. Chapter 6 was applications of the derivative. I feel the book is wrong in doing applications first and then techniques of integration second. We're doing the opposite. We will come back to chapter 6. So first of all, if I let u be this and dv be that, this integral is the integral of u dv. So that's my left-hand side here. If u is x, then du is dx. And if dv is this, what function v gave rise to a dv of e to the x dx? Right? Or what is the antiderivative of e to the x? Right? Antiderivative of e to the x is e to the x, right? If v is e to the x, then dv is e to the x dx. So this integral, which is the integral of u dv, is equal to uv x e to the x minus the integral of v du minus the integral of v du. Let's finish that up. Antiderivative of e to the x is, again, just e to the x. Throw in your arbitrary constant, and you're done. Let's verify. Is this correct? If you differentiate, this is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Minus the derivative of e to the x, which is e to the x. These cancel out nicely, leaving you with x e to the x, exactly what you started out with. You do have to integrate the second part, right? The integral of v du. This is still an integral, so this still has to be integrated. But hopefully, by having chosen the right form of u dv, this second integral should be theoretically simpler than the original. Let's take a few examples. How do we pull out the UV? Here's the formula we're working with, this integration by parts formula. The UV doesn't have an integral there. Could we do multiple of those? I'm not sure what you mean there. Do you mean more examples, or do you mean something else? Let's consider this one. Again, why do we not have an integral there? Well, I mean, you have to look at the integration by parts formula that we derived, right? We did the product rule. We did the product rule, and we got this we got this equation here from integrating the product rule. I'll invite you to have a look at that. I mean, I've rubbed it off now, but we had derived the actual integration by parts formula. Consider this. You're thinking to yourself, if this wasn't there, the integral would be very easy. Matthew's asking if we have something like a product rule. Inside of a product rule, there's no need to view it that way. It would just be a product rule. And, you know, I mean, keep in mind that while this integration by parts formula is the inverse operation of the product rule, you don't need an actual product to apply the integration by parts formula. And we'll see an example of that coming up. But consider this. The idea is, if this wasn't there, the integral would be relatively easy. Let's get rid of it by letting u be that and dv be the rest. If u is pi minus x, what is dv? Why didn't we say du equals 1? Du equals 1 dx. That's fine. Nothing wrong with that. I mean, if there's nothing there, it's understood to be a 1. dv is the rest, right? Because this integral has to be the integral of u dv. So u dv cosine of pi x dx. And consequently, if u is this, du is negative 1 dx. And v, what is the antiderivative of this? Sophia is asking the obvious question, when do you know to use u substitution or integration by parts? And the answer is, Michael is giving us the answer for this, sine of pi x over pi, or 1 over pi, sine of pi x, thank you. But the answer to Sophia's question, how do we know when to use u substitution or integration by parts? Experience. Experience is the answer. Nobody knows. Nobody knows. And if I throw out an arbitrary integral, how do you start? You have to have an idea. You have to have an idea, and you get ideas by practice. Lots and lots of practice. And eventually you recognize what could be done. And you know, I mean, sometimes it's not obvious at all, and you know, you try something. Let's finish that up here, right? So everybody comfortable with this V here? right? If you take the derivative of that, derivative of sine is cos pi x times the derivative of the inside, which gives you a pi, canceling with this one, so you're back there. If you don't see it, and you go from here to there, do a u substitution. It's the integral, right? You do a u substitution. Would there not be a constant when you do the antiderivative? Again, the constant will not play a role here. You can convince yourself of that. Throw it in, see what happens. It's not going to play a role in the same way that it did not play a role in the definite integral. So this, the integral of u dv, this is uv, 1 over pi minus x sine pi x, uv minus the integral of v du. So minus minus, can I change that to a plus? Right, because dx is negative du, so minus minus 1 over pi sine pi x. Everybody comfortable with the plus here? Which is really minus minus, yes? Let's finish it up. So first of all, you see that this second integral is simpler than the original one, right? In the original one, you had an x times a cos. Here, you just have a sine. So the integral is getting simpler. Antiderivative of this, negative 1 over pi squared cos pi x. Throw in your arbitrary constant and you're done. Absolutely, thank you, Victoria. It's plus because it's minus, 1 minus here, and 1 minus from here, right? This dx is negative du. How did you get that initial equation? This one here? We proved that. I mean, I've rubbed it off now. But we proved it from the product rule. Why is it pi squared? If you don't see the antiderivative here, you can make a u substitution. W equals pi x, so that dw is pi dx. How did you get the equation with the plus? It's actually minus minus, right? Minus minus, right? Because the dx is my. I'm not reading that over there. The du is minus dx, so you have a minus dx. So minus minus becomes a plus. Where's the rest of the equation from? How did I get a 1 over pi squared? Do a u substitution if you don't see it. Let's call it a w substitution because I've already used the u here. Right, so w is pi x, dw is pi dx. So this integral, which was 1 over pi, you get another 1 over pi dw, and you get sine of w. I'm introducing a w for those who don't see how to find the antiderivative of that. If you see it, it's fine. On an exam, I would like you to show all the work, so show the U substitution. Consider this. We're going to do integration by parts on this. What are we going to take for U? What are we going to take for dV? Right, you've got lots of choices here. Even if you've settled on integration by parts, there are probably a lot of choices for U and dV. You should show all your work. U is 1 over x squared. So if you settle on U being 1 over x squared, that means that dV has to be the rest. dV has to be ln x dx. And in that case, du is minus 2 over x cubed dx. And what is v? What is the antiderivative of ln x? Some people are going to say 1 over x, but that's incorrect. 1 over x is the derivative of ln x, not the antiderivative. What is the antiderivative of ln x? Nobody knows. Nobody knows what the antiderivative of ln x is. This is not the way to go. Some people are suggesting to switch them. U is ln x, and dV is the rest. And the derivative of ln x is 1 over x. So that works out nicely. And the antiderivative of dV is negative 1 over x. So that was easy too. So you see, Mahar is asking, how can we figure out if we just need to assume U and when both U and dV? Well, I mean, the integral has to be U dV, right? So, I mean, if you're assuming a U, unless you meant the U substitution, And Michael is bringing up an interesting question, which we're going to do right after this one. But let's just finish that one up. We've made this UDV business, integration by parts on this. So UV minus 1 over x ln x minus the integral of v du right? U minus the integral of v du. It's always the same integration by parts formula. The minus cancels again. So minus 1 over x ln x. Integrate 1 over x squared. You get negative 1 over x. Throw on your arbitrary constant, and you're done. There it is. Well, the antiderivative of 1 over x is negative 1 over x squared. So minus gives you the plus again. Again, convince yourselves that this is correct by taking the derivative. And Michael was bringing up the interesting question, what is the antiderivative of ln x? What's after the integration sign? Minus, minus, and I'm suggesting they both cancel out. The integral of ln x. What's the difference between these kinds of problems and previous ones? I don't know what you mean. I'm introducing a new technique here, integration by parts. Before that, we were doing the U substitution. So these are two different techniques that allow us to find antiderivatives. And that's what we're going to study for the next few weeks. Techniques of integration. Methods you can use to find antiderivatives. And consider this, I was suggesting that we don't necessarily need to have a product in order to use the integration by parts. And this is a very nice example. First of all, convince yourselves that, somebody's bringing up the interesting point. A lot of people want to say that it's 1 over x plus an arbitrary constant, but it is not. It is not, because 1 over x is the derivative of ln x, not the antiderivative. So this is incorrect. And if you do that on the midterm, it's going to tell me that there's confusion. And if the marker thinks you're confused, it's not going to go well, as far as marks are concerned. I was suggesting that we were going to do integration by parts. You might try U substitution. What would you take for U? I'll let you work that out. X to the power U. But instead, we are running out of time. So we're just going to go with the integration by parts. And Michael has suggested, you've only got the one function, ln x. You've only got the one function. So if you decide that it's going to be integration by parts, you have to use U as that function. Otherwise, if that function goes in the dv, then you have to integrate this, and that's the original question anyways. So there's really no point in doing that. So here, if you've just got the one function, it has to be the U. Don't split that up into ln times x. Ln doesn't work that way, right? Ln like this is meaningless. It's like a square root. This doesn't mean anything. You need an argument here. It's got to be square root of something. Right, so the integral should be the integral of U dv. U dv is what's left, and there's only dx left. If U is ln x, du is 1 over x dx, and v is x. Integration by parts formula, this was u dv. U dv is equal to uv minus the integral of v du. V du. Or the integral of 1 dx. Antiderivative of 1 is x. Throw in your arbitrary constant, and you're done. Can we verify? Take the derivative. Take the derivative of this, see what happens. This is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. So you get your ln x. Plus, leave the first one fixed, differentiate the second one. Derivative of ln x is 1 over x. Minus derivative of x, which is 1. And this is x over x, which is 1. These cancel out nicely, leaving you with ln x exactly as expected. It's very nice indeed. How are we doing here? Questions? So this seems like a good place to end. Practice this integration by parts business after class tonight. Tomorrow, we'll pick this up again on Thursday. Thank you all for coming. And watch to see what happens with GME. We'll discuss that again on Thursday. You guys have a good one. I will see you then.